We previously discussed how to write the equation of a line using vector form, and obviously we move from vector form to parametric and Cartesian. Now we can elevate that and apply it to a plane as well. So a plane such as this, we know it contains certain points, we know it contains several direction vectors and so on, but we want a way to represent a plane. So a nice equation, a vector form equation that will represent the plane. Now there are different ways to represent it and different initial type of information that you'll be given. So I will deal with every case and every type of example, and hopefully that will cover all the bases for equation of a plane. So the idea is if you have three non-collinear points, so let's say you have a point B here as well and a point C. So if you have three non-collinear points, so they don't lie on the straight line, and point B could have a direction vector of B and point C could have a direction vector of C, then I can define a unique plane that passes through a point A and is parallel to two direction vectors. Quite similar to a straight line. The equation was always so it would go through a point and it has one direction vector, but for a plane you need two direction vectors, so that's the main difference. So how do we start that? So in general you only need certain points to define a unique plane, and based on what you have. Now, there are four types of questions that would show up, and they would require you to find the equation of a plane. Now, you might start off with three non-collinear points, or a question might give you a position vector and two direction vectors, or a question might give you the normal vector and the to the plane and just one point, or it would give you a point and then it would describe your line as being parallel or perpendicular to another plane. So based on each of these information, you should be able to write the equation of the plane. Now, it's a bit overwhelming, a lot of information, a lot of different techniques with each type of question, but as I go through the slides, hopefully I will put it all into one diagram to help you figure out which direction to approach the questions. Let's first actually discuss what to do when you have three collinear points, or when you have one point and two direction vectors. So you'll see the proof starts with this, and then the proof heads to this situation. So there are questions where you're given this immediately, or you need to start from the raw piece of information, which is three non-collinear. So the proof starts from type 1 and then goes to type 2. So let's use the initial image. If I have this plane, you can see I have a position vector A here, and then the idea is we have A, B, and C are non-collinear, and we have points B and point C. They're not on the diagram, but from those three collinear points, I'm going to pick A as my position vector. This is arbitrary. You could pick A, you could pick B, you could pick C, but I'm going to pick A as my position vector, as the clear point that my plane goes through. And then I will say that point B and point C will have a direction vector of B and C. So these two are my direction vectors. So to clarify, this is my point on the plane, and this is I'm just going to write dv. These two are the direction vectors that are on my plane. And we can find the direction vectors using, so B would just be AB, and C would just be A to C. Now, to define this plane, just as we did for a line, I'm going to pick an arbitrary point R on the plane, and I'm going to write a way to define this R on the plane using the three pieces of information that I have. So we start off with, well, I know that AR, A to R, is basically taking the position vector R minus the position vector A. But I also know that AR can be found by a linear combination of AB and AC, which is just the vector B and the vector C. So a linear combination of them, each of them having a different or maybe a similar scalar a scalar multiple. So remember that if you have, so these are real numbers, if you have these direction vectors, since they are non-collinear, the points themselves are non-collinear, I can just do a linear combination of them and it will give me the point AR. So using these two facts, I now have two ways to represent A and R, and I will equate them to each other. So I have R minus A is equal to the linear combination of vectors B and C, and then I can simply move A and make R the subject. So now I have that my arbitrary point R can be defined using the point A and a linear combination of the direction vectors B and C. So basically that last line is the equation of a plane. And this is the vector equation of the plane. So therefore the vector equation of the plane can be written as this, where you have two scalars, lambda and mu, for example, and A is the position vector and B and C are direction vectors. So this is very important to point out. The position vector is arbitrary. I could have started with B as my position vector and then did two different direction vectors. That's fine. But for convenience, we're just using A, B, and C. Now for parametric form, it's similar as writing them in it's much easier if you can see them in component form. So the equation of the plane can be written as such. If I write it in component form, and then to convert it to parametric form, just as we did with the equation of a line, you're taking the each value, so x value, altogether you have a1, alpha b1, mu c1, and so on for the y and the z. So this would be in parametric form. Now for Cartesian form, it's slightly complicated. We have two different ways of getting an equation of a plane in Cartesian form. Either we have to do some algebraic manipulation to this, where you have to deal with this like a system of three equations. And you have to eliminate the lambda and the mu, both of them, using all three equations until you end up not actually solving the equation. You just need to end up with something like this in general form, which is a Cartesian form. Another way to get Cartesian form is from the type 3 of the initial information. So if you're given the normal vector to the plane and the point, this version of information given, which is different from type 1 and 2, this type of information can help you find the Cartesian form easier. So just to distinguish between them. Now before I get to type 3, I'm going to first show you examples on how to solve when you're given 3 non-collinear points or 1 point and 2 direction vectors, and get them to all the 3 different forms. So let's start with this example. I have a plane that passes through these 3 points. I need the vector equation, parametric, and Cartesian. Now you first need to start, remember that these are points, these are not vectors. You need to start establishing creating the information. So this is you starting with 3 non-collinear points, and I need to pick one of these to be my point that my plane goes through. So for convention, I'm just gonna pick A as my point, and then I need to create 2 direction vectors. These are not direction vectors, these are points. So I know that if I have this point A, so this is my point, and I need the direction vector, so I need this that will get me to point B, and I need it to get me to point C. So I need these 2 direction vectors, or they are AB and AC. So I will start finding my direction vectors. So AB would just be 2, 0, -1, take away 1, 2, and 1. And that will give me 1, -2, and -2. And then same thing for A to C. I'm going to skip the steps. So 2, -3, and 1. Sorry, -1. All right, so I have now I've moved from type 1 to type 2 information, which is I have a point here and 2 direction vectors. So sometimes the questions might start off immediately giving you this information, or they might ask you to take the long route, which is you have 3 points and you need to find the 2 direction vectors. So you need the direction vectors. So now I can immediately write the vector equation of the plane. It will be x, y, and z. You can write them in any form, component form or algebraic form. So I will pick my point A, which is 1, 2, and 1, plus a lambda. The order of lambda and mu are arbitrary. You can pick any scalar. And mu 2, -3, -1. Just quickly indicate lambda and mu are real numbers. And that's it. That's the vector equation of a line. And then parametric, quite straightforward. You have 3 systems. So x is equal to 1 plus lambda plus 2 mu. Y is equal to 2 plus minus 2 lambda minus 3 mu. And z is equal to 1 minus 2 lambda minus mu. So we've done part B here. Now I'm leaving enough space for part C because it's gonna take up space. In part C, again, if we have the normal and a point, as I said, the type 3, if we have this version, then it's much easier to do. So if we're in this situation, it's much easier to do, but we're in this situation and it will take a bit of algebra work. So what you have to do is you have to cancel out the lambda and mu. You have to eliminate them, but you have to use a combination of all 3 equations to do that. So there are different algebraic ways to do it. You'll find different methods. As long as the algebra is correct and it falls through nicely, then you've done it correctly. But again, remember, you have to use all 3 equations and end up with 2 equations that you can use. So what I'm going to do is I will take, so let's label them as equation 1, 2, and 3. And what I'm going to do is I'm going to take 2 and 3 and I'm going to subtract them from each other. So this will give me, just because you can see the lambda is has the same coefficient, so by subtracting them from each other, I end up cancelling out the lambda at least. So by doing that, I end up with y minus z equals to 1 minus 2 mu. Now what you want to do is make the scalar the subject, because you want to end up cancelling the scalar. So use 2 equations, eliminate one scalar, and then make the other scalar the subject. That's your goal. So I'm gonna end up with 1 minus y plus z over 2. I'm using equation 2 and 3. Now I need somehow to use equation 1 because you need to use all 3 equations. And I can see, well, I can double equation 1 and add it to equation 2, for example. So I will do 2 times equation 1, and I'll take equation 2 and I'll add them together. So I'm just gonna skip the long steps. So this will give me 2x plus y and 4 plus mu. So this will end up eliminating the lambda as well, which is what we wanted. So you want to eliminate the same variable when you're doing this step. And then same thing, you want to make mu the subject. So that will give you 2x plus y minus 4. So now I have two ways of writing mu. I can make them equal to each other, and that way I would have cancelled the mu out, which is what we needed. So hopefully the idea behind this is clear so far. So making them equal to each other, I have 2x plus y minus 4 equals 1 minus y plus z over 2. Now it's just algebra work. And then we end up with and then to get it to Cartesian form, you want all the x and y and z into one side, and then your constant on the other side, for example. So by simplifying that, we end up with plus 3y minus z is equal to 9, and that is your equation in Cartesian form. So hopefully it was clear with Cartesian. It's not an unusual new thing. You would have done it in system of 3 equations. So pick one, one method to do it is to pick one scalar and eliminate, but you have to use a combination of all 3. So use one pair and then another pair, and then you end up with 2 equations with the other scalar being the subject, and then you equate them to each other, and that way you would have cancelled the other scalar, and then you end up writing it this way. Remember, we're not trying to solve the equation, we're trying to write it in Cartesian form. Now, what about the normal? Well, if I'm given something that's normal to the plane and a point on the plane, so how would I actually solve this? If we define the normal, we know it's perpendicular to every point on the plane, including AR, this arbitrary R that we're going to pick. So we know that if we take the scalar product of 2 perpendicular vectors, the answer is going to be 0. This is where the scalar product is helpful. We did something similar with the equation of a line as well. So if I take the normal and the point AR, I know it's going to be 0. Well, what is AR in this situation? It's R minus A. And then I know I can expand out based on the properties of scalar product. So by multiplying out, I get the following, and then I can move n scalar product A to the other side. And this is my equation of the plane using the normal. Now, R is going to be your x, y, z, and your A is going to be the point given. And the normal, again, will be given in the question. Well, either given in the question or I'll show you how you might need to find it. So how do we write it in Cartesian form? Why did I say that the normal is a helpful piece of information to write something in Cartesian form? Well, let's write it in component form and see what we actually get. The same equation as the last line, if I write it in component form, and then I actually solve it. So remember, scalar product's just taking n1 times x plus n2 times y plus n3 times z. So this will give me something with x, y, and z, but the right hand side will actually give me a number. So basically you'll end up with this simplifying to x, y, and z, where a, b, and c, you have coefficients, and then this will end up being a number which will represent this d. So you have the Cartesian form, and it's really easy to find when you're given the normal. So something to note, which is really helpful, which is the reverse basically. If you're given something in Cartesian form, such as this, then you can immediately see that, notice how the coefficients of x, y, and z here are basically the normal of your plane. So if you're given in Cartesian form and I'm asking you to find the normal, you don't need to do calculations. It's just the coefficient of a, coefficient of y, coefficient of z written as such. So that's the normal of the equation or the plane. Now, what if the normal is not given, but you are expected to write it in normal form, or you want to write it in normal form? So you can do that by taking the 3 collinear points. If you're given the initial information as 3 collinear points, but you want the normal, what you do is you find the 2 direction vectors, like I showed you in the first example, And then you take the cross product, because remember, the cross product of two vectors results in a new vector that's perpendicular to both of them. If you go back to vector product, I'm writing cross product here, but it's also vector product. If this is A and this is B, then the cross product of them is the cross product that you get is a vector that's perpendicular to both A and B. So that's how you get the normal. So if you're given 3 collinear points, you find the 2-direction vector, find their cross product. Or if you're given 1 point and 2-direction vector, then immediately take the 2-direction vectors and find the normal, the cross product. And the result that you have will basically be your normal plus the other points that you have from the initial information. So let's try it with this. So it's the same numbers as the previous question. This example 1, a plane passes through these points. I want the Cartesian equation using the normal vector. So they're clarifying that for you. We won't go through finding vector A and B. We've already done that, but this is what I mean by when you're given 3 initial points, find the direction vector, and then I need to find the normal using cross product. So taking the normal, I have 1 minus 2 minus 2, and cross product with 2 minus 3 minus 1. I won't go through the math, you can go through that, and it's going to give you minus 4, minus 3, and 1. Now, you can stick to this, but then you'll realize, well, actually, it will look nicer if your x and y are positive. So keep in mind that if this is your normal vector, if I take a factor of -1 out, it will give me 4, 3, minus 1. These two are parallel to each other. So it's like saying, well, I have a plane here. This is the normal -4, -3, and 1. And then this is another one that's parallel to it. Well, if it's parallel to the initial normal vector, then it's also perpendicular to the plane. So both of these are normal vectors to the plane. The normal vector is not unique. The equation of the plane is unique. So the normal, the setup of the plane is unique, not the equation of the plane. So I have -4, -3, and 1, and 4, 3, minus 1. They're parallel. It's just that I took a scalar factor out. So I can actually use this as my normal vector because it just looks nicer. So then setting it up, it was, remember, R and then N with a point A. So I will take 4, 3, minus 1, and then X, Y, and Z equals 4, 3, minus 1, and then one of my point will be A, so 1, 2, and 1. This will end up being 4x plus 3y minus z. And then on the right hand side, you can evaluate the scalar. So go 4 times 1 plus 3 times 2 plus -1 times 1, and that's going to give you a 9. And if you notice, it's the same answer as we got from the previous slide. Here, 4x plus 3y minus z equals to 9. But this was a longer method, and when you have the normal, as you can see, it's much shorter. Now, I give you a lot of information, a lot of different methods to approach. I summarized this into a nice diagram. Hopefully it's going to help you know how to move from different type of form to another based on the information you have. Well, you first know how to write a vector equation, you know how to move to parametric, and then you know how to move to Cartesian. If you're given 3 collinear points, you always have to move to 1 point and 2 direction vectors. So you pick you need to find the 2 direction vectors. From here, you can immediately write it in vector form and then so on, get to the form that the question wants. Now, if you're in, or they might give you 1 point and a normal, which means you can immediately go to Cartesian form. Now, if you're given 3 non-collinear points and you need it in 1 point and normal, you first need to find 1 point and 2 direction vectors, and then you do 1 point and normal. And from 1 point 2 direction vector to 1 point and normal, you need to take the 2 direction vectors and take their cross product, and that will give you 2 the normal. So in here you can say you need to take the cross product or vector product of two direction vectors, and in here you need to find two direction vectors to move from here to here, and so on. So hopefully this makes it easier to use the initial information. Now, what if I'm given something like, oh, it's parallel to another point, or perpendicular? Perpendicular, you just use the normal, but what about parallel? So I have a plane, but it contains line 1 and is parallel to the direction vector of line 2. Well, how will we deal with that? So I still need my information of 1 point and 2 direction vectors, or a normal, for example. Well, I know if it contains L1, it means it contains the points on L1. Well, this is a point on L1, so I know that this is the point on my plane. And if it contains L1, it means it also contains this direction vector. So I know this direction vector exists on my plane. But I know it's parallel to this direction vector as well. Okay, so notice how I have 1 point and 2 direction vectors. So I am in this situation here. But then they want it in Cartesian form, and it's much easier to find the 1 point and normal now. So based on what I have, I will first find the cross product of the 2 direction vectors. So the rest of the solution is quite easy to do. The trick in the beginning was just to figure out what points to use, or what vectors to use, sorry. So the cross product here is going to be 3 minus 1 minus 2. And then to write it in Cartesian equation, I need to take the normal with the x, y, and z, the scalar multiple, the scalar product, and then times my point, which is 1, 2, and 3. This will give me 3x minus y minus z minus 2z. And on the right hand side, 3 times 1 plus minus 1 times 2 plus minus 2 times 3. Simplify that, that's going to give you a negative 5. So that's the Cartesian form of my plane. Now we've covered everything. This next question is a bit extra. You can have a go at it, or you can stop the video if everything is clear. But I just want to add it in there because it's a question with several parts, so I wanted you to have a look at, well, what if the equation of the plane is given, but I'm asked to find different pieces of information. So I'll go through that quite quickly. Now, finding the normal, we said, remember a few slides ago, that if you're given the equation of the plane, remember that the coefficients of your x, y, and z are the normal vector. So the normal vector is basically 3 minus 2 and 1. Or you can write it as 3i minus 2j plus k. Alright, so that's for part A. Now, find 3 points on the plane. How would you do that? So it's just like when you have y equals to mx plus c, and I'm asking you to find 3 points on the line. All you have to do is just substitute a couple of points. And we want a nice way to do that. Basically, what you're going to do is you're going to replace 0 for 2 letters, and then you figure out what the third letter is going to be. So quite easy. So if I make x, so for part B, if I make x and y 0, I could do that. Then it gives me z is equal to 6. So one of my points on the line is 0, 0, 6. And then if I pick x and z to be 0, then it's going to give me a negative 2, sorry, not negative 2. We have 0, minus 3, 0. And then if I make y and z 0, so basically you're just substituting here. It will give you 3x equals to 6, and then you solve it. You get 2, 0, 0. So I can call this, since this is x, I can call this point A, and since this is y, I can call this point B, and since this is z, I can call this point C. So I have 3 points on the plane here. So it's like starting with, oh, I have 3 non-collinear points here. Part C wants you to find 2 vectors that are parallel to the plane. Well, I have points on the plane. If I find the direction vector, they will obviously, by definition, be parallel to the plane. So I can just simply find AB and AC, for example. I'm not going to go through the maths, but AB is going to be -2, -3, 0, and AC is going to be -2, 0, and 6. And then part D confirmed that the normal vector is perpendicular to both of these, and you can easily do that by doing the scalar multiple. So 3, -2, and 1 with a dot product of -2, -3, and 0, and you'll notice that it's going to give you a 0. And you can continue the same thing with C. So you need to show both of them. Write all the forms of the equation. We have it in Cartesian form already, which means in vector form, we have it as x, y, and z. We can pick one of our points, which is 2, 0, 0, and then we can have one of the direction vectors, -2, -3, 0. Remember, direction vector, not point. And then mu, -2, 0, and 6. And we have lambda and mu being real numbers. And then in parametric form, we have 2, -2 lambda, -2 mu. And then Cartesian is basically what they give us. So Cartesian form, you can write it again if you need to, but obviously not necessary. You can double check as well that it works. You can set up the normal multiplied by x, y, and z equals to the normal, not multiplied, I mean scalar product with 2, 0, 0. And it's going to give you the same answer as above, 3x minus 2y plus z equals to 6. So this is the other form. So hopefully this is clear. The only thing you need to be careful about with equation of a plane is what type of information do they give you initially, and how you can use those information to set up the equation and the form that they're requiring.